As I said, I've been working with the team of Professor Karen Scrivener since 2005. This is where we started the research, and in 2008 we came across this synergy between limestone and calcined clay, which gave origin to the LC3. And there's a lot of people in this team working on the science. My role has been to do a little science, but also connecting the academy and the industry. And we are currently working all over the places but the Americas, so my idea is to focus more on the Americas. Well, Sofia already spoke about me. I have two hats. My first hat is as a professor at the university in Las Pillas, where there is a research center called CDEM, and I am the head of this center. And the second hat is as a private consultant from the company, the Swiss company EcoSolutions, and through this company we interact with clients, customers all over the world. I also am very active in Innovandi, which is an initiative from Global Cement and Concrete Association, GCCA, and in Ryland, which is the global network of Building Materials Lab. I share the technical committee 282, which works on calcined clay, so that gives me the possibility of having an overview of what everybody's doing around the world, how things are moving, academy, industry, etc., etc. This is our team. So we have two what we call technology research centers. One is located in Cuba, and it's attending the region, Latin America, North America, a little bit in Africa also. And then we have another TRC, which is in India, in the Indian Institute of Technology in Delhi, and they are attending all of the, especially India, but also outside India in Asia. And the head of this is an EPFL, and this is Professor Karen Scrivener, who was the head of the entire project. This phase of the project, we have been pleased to be funded by the Foundation Climate Works in the U.S., and this is enabling us 2 more years of work interacting with the industry. First of all, discussing about the sustainability in the cement industry, I mean, we're seeing there are many things going on. There was a big discussion with Tomayo on the carbon capture and utilization and storage. Of course, we will be forced to do that, but the cost of doing this is very high, especially for some developing countries. I mean, it's going to almost double the price of the cement if there's no subsidies covering this. And of course, you can improve the efficiency in the kilns, but it also has a cost. And the most interesting alternative in the short term, because also Karen explained that we need to react very quickly if we really need to mitigate that, is the clinker substitution. The problem we have is that we have been using for more than 30 years these industrial byproducts like slag, fly ash, everything, but because of the measures to mitigate the climate change, these materials, the availability of these materials will decline in the near future, because coal power stations will be shut down, hopefully, and the industry will recycle more material, so there will be less slag, and so this is the scenario. And the other options we have is natural pozzolans, which are, you know, limited geographically. For instance, in countries like Costa Rica, Guatemala, you have very good natural pozzolans, but in other countries they don't. And also limestone, which is widely available, but it's not reactive. I mean, these are the challenges. If you look at the region in Latin America, we have, for the general use cement, we have a very low clinker factor. And this is very interesting. Compared to the rest of the world, we are very good for the general use cement. But when you look at the clinker factor for the cement that we use for structural concrete, ready-mix concrete and everything, we're still very high in terms of clinker factor. So around 85%, meaning we still, and this is roughly 35% from the cement that is used in many of our countries, so we need to do a lot there. And this is where LC3 can really do a major role. So how to respond to this? I mean, we have this option, we have other options, but in our case here, we're focusing on LC3. Karen already explained that, so we're able to replace 50% of the clinker and yet have the performance in all ages of a same one. We're now, and this is rather new, we're now exploring, moving the boundaries further. So we're now trying to work with cements that have 35% clinker content. I'll discuss that more in detail. And so the important thing here is that, and this is the magic of the LC3, is that we're having a reaction between calcined clay and limestone. Another reaction. We're still, calcined clay is a pozzolana. It is reacting with the clinker. But further to that, we have the reaction with the limestone to produce an alumina phase called carboaluminates that is replacing the monosulfates. And by doing this, it is stabilizing the ethylene guiding system. So at the end, you have a system where with less clinker, so filling the pores is not related only to the reaction of the clinker phases, but also to the reaction between the limestone and the calcined clay. This is why you can afford to have a lower clinker content. This is why when you compare different clinker factors, 65, 50%, you have almost the same results, because clinker here is no longer the most important factor in these systems. And also another important thing is when you compare there, this is a way of comparing the reactivity of the different pozzolanas compared to calcined clays, because sometimes people in the industry tell me, well, if I have natural pozzolana, which I don't have to calcine, why should I use a material where I have to spend energy? I mean, calcine this material. Well, I can respond that because it is a highly reactive material, extremely reactive material. If you compare this is the orange, and the width of this band is it goes from the poorer quality clays to the high purity clays, and there, when you see in the middle, it's talking about 40%. Meaning a low-grade clay with 40% kaolinite content has the same reactivity of silica fume. Can you imagine? Silica fume costs, I don't know, $900 a ton, $1,000 a ton, where in calcined clay you get it for, I mean, roughly $15 to $20 a ton. So this is the reason, and don't even talk about natural pozzolans, about fly ash, about slags. I mean, they are very well below in the scale of reactivity these materials. So the higher the reactivity of the supplementary cementitious material, the more clinker you can replace in your system. And this is also something we have to understand from the chemistry of the system. And there you see, for instance, this is a very interesting exercise I did a few years ago. I was plotting information from the literature, different systems, I mean, quartz, limestone, fly ash, slag, natural pozzolana, and I was, this is the ratio between the strength of the blended material and the strength of pure cement. And you see the only ones that go above 100% are the ones containing calcined clay. And this is really very, very interesting. But also, if you see this map, Karen presented that already, and I was able to plot the cement plants, and I was able to, near the cement plants also, you have the limestone there. Of course, wherever you have limestone, you have cement plants for the clinker. And you see that also the distribution of the kaolinitic clays is very, very, associated with cement plants. So normally, I can bet that in the radius of 50 kilometers away from the cement plant, you can find suitable clay. So this is also a very important issue. So, but very often when I go to the cement companies, the geologists, and I have here some of the geologists I started working with, their first response is, we don't have these clays. I'm sorry, we don't have the clays. Why? It's very common. Geologists, they are trained to find clays with a high silicon content and a low alumina content because they want to make clinker. And our clays, those are the so-called 2-to-1 clays. And our clays are totally the other way around. They're high in alumina and they're low in silicon, because we're talking of the one-to-one clays that Karen already explained. So this is very, very important. And we have been able to, you see, all of these dots are the clay candidates we have tested throughout these years. I mean, we have tested more than 200 candidates of clays in more than 25 different countries all over the world. And we have seen that there's an empirical criteria that you can have. I mean, this is a rule of thumb for the selection of a clay. You can say, if you have alumina higher than 18%, and if you have a ratio between the alumina and silicon higher than 0.3, and the losses on ignition higher than 7%, you are very likely to be there, to have a good material. It's not 100%, I warn you, because you can have these properties with other things. We can discuss that later. Then you have to calculate the kaolinite content by measuring the weight losses between 400 and 600 degrees Celsius. There are several methods. If you have a thermal balance, that's the best. But if you don't, you can use a simple lab furnace like the one you see there. And you would be amazed to see the accuracy of the testing. I mean, the comparison between sophisticated lab testing and this lab testing, and this is really amazing. And so finally, we have developed, so we have the know-how. We know how to bring a company from not knowing anything about the clays to the point where they are ready to start producing the clay. And we have this protocol there. I won't discuss it because for the sake of the time, but this is also very interesting, and it's also published elsewhere, and you can see that. Also, in terms of clays, you have to be clear that you may have sometimes bad quality clays, and you can blend the clays, even within the quarry. But also you can have clays that are very, very high purity, I mean, and you want to save your resources, and you can dilute these clays. And this is an example that you see here. You see on the horizontal, this is kaolinite content. On the vertical, this is the compressive strength. And you see different clays that we're testing and different blends. And this is a real case. I mean, I cannot disclose it's in Africa. Cannot disclose the location, but this is how you see, and it's really amazing what you can see. So you already have the clay, but now you have to activate the clay. It's important to know that the kaolinite, technically, the water is removed at the temperature range between 400 and 600 degrees Celsius. But above 600 degrees Celsius, you have a window of about 250 degrees where nothing happens. Meaning, on the safe side, because you're working with particles and you have to diffuse the heat through the particle and then you have to extract the water from the particle, it's very practical to work at higher temperatures. I always recommend to be around 800, 700, 800, so that you can really guarantee that you take out all the water in the system and you dehydroxylate the material. But also, cement makers are not used to work with clays. Clays, they need a different treatment. So you have to consider the clay preparation line. This is very important, how you mine the clay, how you store the clay, because this is a very wet material. Normally, when it is on the belt conveyor, it has 20% moisture content if you're using a rotary. If you're using a flash calciner, and they will discuss that this afternoon, you have to dry the material in order to be there, and you have to grind it too. So there are different choices technology-wise. And also, as I said, in a short period of time, in less than 30 minutes, you can activate the material, provided it reaches the chamber, either in a rotary kiln or in a flash calciner. I mean, I won't discuss neither of those because there's going to be presentations on a panel this afternoon discussing about that. But we have to bear in mind that during the calcination, there's some transformation of these particles, for instance, agglomeration. And that plays a major role, and we have also here the admixture companies with us, plays a major role also in terms of the water demand of the system. Because in these agglomerates, you can trap water. And this is further to the electrical charge and the other things that are taking place. You also have to deal with it in this. One of the strategies that companies are using is firing at higher temperature to reduce the water demand. But then when you do so, you're compromising the reactivity of your material. And also the other thing is when you have iron in your clays, because remember we're dealing with low purity clays, normally you have many other accompanying minerals like iron phases, normally as hydroxides. And if you calcine the material from more or less 650 on, regardless the availability of not of oxygen, you only form a magnetite, which is a black material. But during the cooling, if oxygen is available, this reaction can be reverted and you can get hematite. And this is why you get a very red material when you don't control the atmosphere during calcination. But it's very easy to control that. Well, Karen presented what they're doing. I have a pilot plant. We're doing this all the time. And I mean, it's very, very easy. We can discuss it. It's already published. There's a paper on that. And you can see here, this is a pilot plant I have in my campus. And it's a very simple system of controlling color control. And we can get a more or less black material, depending on how we can control the CO2. And also for reactivity of the material, we have several protocols, but right now the so-called R3 protocol is ASTM standard, so it's very practical and very easy to use in different choices, bound water or isothermal calorimetry, the heat release. So you already have the clay calcined, but now you have to formulate the cement. You have to make cement out of that. There are several things influencing in the cement. First of all, and very important, is clinker. I mean, in the clinker, especially the C3S, which is the one, because remember, at 24 hours, the strength relies only on the clinker phases. The pozzolanic reaction begins more or less at 30 hours, 35 hours. The alumina begins to react and form ettringite. So in the first 24 hours, you need to have a high C3A content in your clinker. But also, if you have a high C3A, also in the second day, you're going to have a higher strength, second, third day. Remember, for the standard in cement, you need 2-day strength. You don't need 1-day strength. 1-day strength is for concrete, for the molding. And also, the alkalis are very important, because if you have higher alkalis within the limits, you can have a faster pozzolanic reaction. So also grinding is very important, especially because of particle size distribution and the water demand that is normally increased in these systems. Also, I will not discuss this because there's going to be a presentation from the admixture producers. And but normally, this is what we're seeing when we did the first industrial trial back in 2013. Because of the electrical charge of the particles, they created a coating through the steel balls in the ball mill, and this coating prevented the clinker grains to be ground finer, and that really compromised the strength, the early strength of the material. Late strength was okay, but early strength was compromised because of that. But the good news is that you can use any of the commercial grinding aids and you can tackle this problem without, very easily. You see here the difference, how the balls, the steel balls look very clean. And also we have been able to test that, the impact, especially the TEA. The products that have TEA as main compound. And there's interesting developments in the industry right now. Hopefully will be discussed this afternoon about grinding aids associated with grinding systems with calcined clays. And the other thing that we're doing is we're trying to make separate grinding. Instead of grinding all together, we do what we call LC2, which is a combination of calcined clay, limestone, and gypsum, which you can flexibly blend with your Portland cement. And this is very interesting because it has a long shelf life. You can keep it there for 10 years, doesn't hydrate. You can even wet it, then you dry it and you can use it. It's a very practical thing, and many producers are now turning into this. This is an example in Cuba, for instance. We're getting strength in the range of 80 MPAs, 80 to 90 MPAs with this concrete with only 350 kilograms of cement per cubic meter. So those are real results performed by a foreign company working in Cuba, building hotels and everything. They were using this material in practical applications. So we see two potential applications right now. The first one is an LC3 with 50% clinker for structural applications like ready-mix concrete and everything. And we also see an LC3 with 35% clinker content for general use applications. So in both cases in the region, we will be able to significantly drop the clinker content and therefore increase the carbon savings in the system. For the first system, I mean, there's no other pozzolanic material that compares. So here, this is a comparison between calcined clay, slag, fly ash, even combining with limestone and everything. And in all cases, you see the brown colors are the calcined clays, and we are always, and you see the standards also. We're always meeting the standards. We're always, fulfilling all the conditions needed. But very interesting, also, we tried to drop the clinker content down to even 25%. And you realize that if you have 35% clinker content and you have a relatively reactive material, you can get decent results meeting the standards of a general use cement and making a significant reduction in clinker content. And we are within the standards because the ASTM since 2014, they launched the C595 that enables clinker content down to 35%. And the EN 197 issued the fifth part of this recently, which enables clinker content down to 50%. So on the standards, we're covered and we have the potential. And in terms of concrete, I'm just giving you an example of a concrete made in a concrete plant, a ready-mix plant in Cuba. It is actually a prefabrication plant. You can imagine it is out of the date, the technology, very primitive, very thin, it's very robust. We were able to get 17 MPAs at 24 hours with only 250 kilograms of Portland cement per cubic meter. So this is really, and at 28 days, we were able to go above 50 MPAs in terms. So now this concrete is for a girder that is in a bridge offshore in Cuba, and we have sensors there. We're measuring the performance of the material. In terms of performance, you can see here the test that we have done for the standards, where we have tested different cement contents, different water cement ratios, and for those we have tested the strength. You see the brown are the calcined clay and the gray is Portland cement. In all cases, you see we have similar strength, but in terms of, for instance, surface resistivity, which describes the corrosion performance in terms of durability, we have a significant, more or less factor 8 improvement. And also in terms of the rapid chloride permeability test, we have very good results for the columns. In terms of carbon emissions, Laurent will discuss that in more detail, but just to give you an idea, this LC3 with 50% clinker will be able to save 40% of carbon emissions compared to a same one, to a pure Portland cement. But even with a blended cement, we're able to reduce up to 18% of the carbon emissions. And if we go to this 35%, then we're talking about 40% related to the best benchmark in the world, which is quoted by GCCA. We can reduce 40% of the clinker content. So I'm coming to the end of my presentation. This is not only a development in the lab or an academic research. We have industrial applications. You see all of this. In this map, we are picturing all the companies that have publicly announced that they're building workshops. There are some of the plants already in operation. I have a small plant, pilot plant at my university. It's, it's a tiny toy, But then Argos they opened a plant in Colombia a few years ago, and also Simpor, they have this plant in Ivory Coast, and there are a few plants now being announced for the, so with this I come to the end of my presentation, trying to summarize this. I mean, the combination of calcined clay and limestone is the path for sustainability because of the availability of material, because of the low clinker factors that you can receive, because you can still produce a high quality cement. There are many options for different actors. There's technology available. We will see this in the afternoon. And we will be able to reduce, to make a significant contribution to carbon emissions by reducing more than 40%. And this is not a theory. This is not a Discovery Channel documentary. This is real life. This is happening right now in life, and we will also see in the afternoon companies that are producing calcined clays already. Thank you very much, and I'm looking forward for the questions.